Hi everyone, today a video in the thermodynamics topic looking at enthalpies of solution. So we know that ionic solids can dissolve well in polar solvents. We have this idea of like dissolves like. So ionic solids can dissolve well in polar solvents. And in order to dissolve an ionic compound, we have to break up our solid lattice of those ionic bonds between oppositely charged ions, like electrostatic attraction. We have to put energy in to break that apart. And we saw in the previous video that we could define an enthalpy of lattice formation, where we take our gaseous ions and form 1 mole of the solid ionic compound. Really what we're talking about here for breaking up a lattice is that lattice dissociation enthalpy. So going from our solid, 1 mole of our solid ionic compound to our gaseous ions. And so the energy that we have to put in to do that is our lattice dissociation enthalpy. Now the separate ions, in the case at the bottom here we have our sodium chloride lattice, the separate ions, the sodium cation and the chloride anion, are then solvated by the solvent molecules, usually water. And so these cluster around the ions. And in the previous video we talked about a definition of the enthalpy of hydration. And this is what this is, where we are surrounding these ions with water molecules. And so it's called hydration when the solvent is water. It's a hydration reaction, we would say. And between the ions and the water, we've formed what we call an ion dipole force. And this is because actually water is a polar molecule. And so we have our polar bonds here, our OH polar bonds. We have delta positive on the hydrogen, delta negative on the oxygen. We have this dipole. And overall, water has an overall dipole because of the shape of it, the bent V-shaped molecule that we have there. And so we end up having the delta negative oxygen interacting with our sodium cation and the delta positive hydrogens interacting with our negative chloride anion. So again, it's electrostatic attraction, but now it's not ionic bonds, it's an ion dipole force that has been formed here. So if we have to draw these pictures out, we draw our sodium cation surrounded by waters with the oxygen facing the cation. If it's the anion, we draw it with the waters with the hydrogen facing the anion. Now, the enthalpy changes of hydration show the exact same trends as the lattice enthalpies of formation. So in the previous video, we talked about the lattice enthalpy of formation, and we saw that because essentially it's an electrostatic force, the smaller the ion is and the larger the charge, the more negative the value of lattice formation. We said it was essentially a bigger number, but because lattice enthalpies are exothermic, energy has been given out because it's an attractive process putting these ions together. We've made bonds that we have a negative number, and so it's better to say that it's a more negative value. And so this was that the smaller the ion was, the closer it could get to each other. In the case of the ion dipole force, this hydration here, the smaller the ion, the closer the water molecules can get. And for electrostatic attraction, the closer the two charges are, the greater that energy. And then obviously the larger the charge, well, that's going to increase the electrostatic attraction as well. And so this gives more negative values of both lattice enthalpies of formation and hydration enthalpies. And remember finally that if we talk about the lattice dissociation enthalpy, breaking apart, this is an endothermic change. We have to put energy in to break that ionic lattice apart. And so therefore these trends of a smaller ion and larger charge give us a more positive, a larger number for the lattice dissociation enthalpy. But the key thing is to dissolve up our ionic compound, we have to put energy in to break the ionic compound, the lattice dissociation enthalpy, and then we have to solvate our ions, our hydration enthalpy. So we can do Born-Haber cycles, we can draw them out for enthalpy of solution. So we talked last time that our enthalpy of solution was essentially taking a solid ionic compound and dissolving it up in water to create these solvated ions, so essentially to create an infinitely dilute solution. We're going to solvate these ions so much that they are so far apart that they don't interact anymore. Remember that the difference between the solvation enthalpy and the hydration enthalpy is that the hydration enthalpy refers to a particular ion, so we can hydrate the sodium ion or we can hydrate the chloride anion, the enthalpy of solution relates to the actual dissolving up of the entire compound. And so if we're going to go for drawing our Born-Haber cycle for this, remember in the previous video, for our standard ionic compound, we said our first step was to always put the elements in their standard states in as our zero line. If we're working on some hydration and solution data, it's a slightly different way about that we go about drawing this. And so we need to think about how do we actually dissolve up an ionic compound. It's the steps we've just talked about in the previous slide. We have to break up the compound, so that's lattice dissociation, and we have to solvate each of the ions. That's hydration. So the data that we need here is the lattice dissociation, the enthalpy of hydration for each of the ions, and then what we're typically going to work out is our solution enthalpy, our enthalpies of solution. And so you can see I've listed these here at the top. So you have the hydration of the sodium and the hydration of the chloride ions. Remember that the definition of this hydration was to go from gaseous ions to aqueous ions to solvated ions. And so we have our sodium ion as a gas going to sodium ion as aqueous. The chloride ion as a gas going to the chloride anion, aqueous. And as we said, these are negative values. Hydration enthalpies are negative because essentially it's an attractive force. We're forming an ion dipole force, and therefore if we form things, energy gets given out. The solution enthalpy of our sodium chloride, remember the solution enthalpy is to take the solid ionic compound and to dissolve it up fully to create this kind of infinitely dilute solution where these ions are so far apart they don't interact. That's what we're trying to work out in this case. The lattice enthalpy can either be formation or dissociation, so I've shown both of them here. Typically a question will only give you one, and it's important to know which one you're dealing with. So remember again that our lattice enthalpy of formation is our gaseous ions forming 1 mole of the ionic solid. So sodium plus as a gas, chloride minus as a gas, going to NaCl as a solid. Remember that lattice formation enthalpies, because we're making bonds, are exothermic, energy is given out. And the last enthalpy of dissociation is breaking up our solid ionic compound into the gaseous ions. So sodium plus as a gas, chloride minus as a gas. And that's therefore a positive number, endothermic, because we have to put energy in to break the bonds. Now again, remember that when we draw out our Born-Haber cycles, that if we have an exothermic process, that's energy being released, and so we draw our arrows going down with forming bonds or an attractive force. That's an exothermic change. If we have an endothermic change, for example, breaking bonds or repulsive interactions, that's a positive enthalpy change, and therefore we draw our arrows going up. So if we now go and draw our actual diagram out, the way that I start these ones is to actually start with the solid ionic compound. So if you remember from the Born-Haber cycles in the previous video, the first step I always said for those was to start from the elements in their standard states, and then to draw the arrow going down, exothermic, for the enthalpy of formation. Remember that the enthalpy of formation is simply forming whatever compound it was, in those cases an ionic compound, from the constituent elements in their standard states. Now from the data we've got here, we don't really have those elements in the standard states, so we don't have to worry about that. But the starting point actually is the very bottom part of that of the Born-Haber cycle. So the very bottom part is the solid ionic compound, like it was in the previous video as well. And so at the bottom, I'm going to write down my sodium chloride as a solid. The first thing I always do is draw an arrow going straight up. What I'm thinking about here is the endothermic process of breaking up this lattice. And so I'm thinking about the lattice dissociation enthalpy. So breaking up that solid ionic lattice into the gaseous ions. And so because I'm going about the dissociation, the endothermic process, I'm going to draw the arrow going up. Now this is why it's important to note what data you're given in the question. If you're given the lattice enthalpy of dissociation, a positive number, then that's absolutely fine. You can just put the number straight in and you can draw your arrow going up. If you're given the lattice enthalpy of formation, an exothermic negative change, then you have to remember that what you actually need here is the dissociation enthalpy. And remember that they are just related by a change in sign. So the lattice formation enthalpy is negative 788 kilojoules per mole. The lattice dissociation enthalpy in this case is positive 788 kilojoules per mole. So if they give you the lattice formation, just remember to essentially flip the sign of the arrow, flip the sign of the actual number. Sometimes questions won't even tell you which one they're going to give you, they'll just say it's the lattice enthalpy, and then it's up to you to use your chemical common sense to look at the number and see whether it's a negative or a positive number. If it's a negative, it's the exothermic, and therefore must be the lattice enthalpy of formation. If it's positive, it must be endothermic and is the lattice enthalpy of dissociation. So once I've done that first step, I've now created my sodium and chloride anions that are gases. And then my next step is to then think about hydration. And remember that we have to essentially hydrate these ions, get our water molecules to cluster around these ions, create those ion dipole forces, and we have to consider these ions separately. So I'm going to draw on the hydration enthalpy for sodium, -406, exothermic, so the arrow goes down. The hydration enthalpy for the chlorine, again, for the chloride anion, again goes down, -363. And notice that when we write our equations, we're just changing the gas state symbol for an AQ, aqueous state symbol. And then the final one is the solution enthalpy. The solution enthalpy essentially is, remember, going from our sodium chloride solid to our aqueous ions, in this case the sodium and the chloride aqueous ions. Now you'll see here that I've actually drawn this as a double-ended arrow. Now you should never ever draw a double-ended arrow in one of these enthalpy diagrams. The arrows either go up or down. But what I'm depicting with this is that solution enthalpies can either be negative or positive. They can be exothermic or endothermic. And it's completely up to the specific example that you're dealing with. If we have a negative solution enthalpy, an exothermic change, i.e. breaking up our ionic lattice into its ions is exothermic, what that actually means is that the attraction between the ions and water is greater than the attraction between the ions and the lattice. I.e. it prefers to be solvated, it prefers to have this to be the ions to be hydrated with the water molecules rather than being in that ionic lattice. Now if that were the case, the line that I've drawn for the sodium and chloride aqueous ions would actually be lower than the NaCl starting point at the bottom. The other example is if we have a positive solution enthalpy. So this is what the example is showing here in this question. Here we have our sodium and chloride ions. The line for that is slightly above the sodium chloride solid lattice. And so we have a positive and endothermic solution enthalpy. What this means is that the attraction between the ions and the water is actually less than the attraction between the ions and the lattice, i.e. it prefers to stay as the ionic compound rather than being hydrated and rather being dissolved up. And so this is the key factor that we're looking at here. Either the ionic lattice is more favourable, and so we have an endothermic solution enthalpy, or this hydrated state with the ion dipole forces and the sort of dissolved up state is more favourable, and we have an exothermic solution enthalpy. So it's really important to make sure that you watch out for the direction and the sign of this, and also for the direction and the sign of the lattice enthalpy, as I talked about earlier. And so again, now to actually calculate it, we just apply Hess's law that the overall enthalpy change is independent of the route taken. And so if we can't go from our sodium chloride solid to the aqueous ions, if we can't go that way going up, we can just go the other way around, so go straight from the sodium chloride solid to the gaseous ions, that lattice dissociation, and then through the hydration steps. And remember, as I said in the previous video, that if you go with the direction of an arrow, you keep the sign. If you go against the direction of the arrow, you have to flip that direction of the arrow, and by doing that, you flip the sign of the enthalpy change. And then simply, we just apply Hess's law, we add all these enthalpy changes together for the route that we're taking. And so if I go starting from the bottom going up to the top, that's the lattice dissociation. I'm going with the arrow, so plus 788. And then I go with both of my hydration arrows, so it's plus -406, plus -363. And then your answer for that comes out actually to be plus 19 kilojoules per mole. Now this might seem a little bit odd to you and a bit interesting. Here we have a compound, sodium chloride, standard table salt. We know that this dissolves up very readily in water. However, what we've just calculated is a positive solution enthalpy change, an endothermic. We have to put this in, and we've put energy in, and we've just said that therefore the attraction between the ions is greater than the attraction between the ions and the water is less than the attraction between the ions and the lattice. So this might seem a bit strange. What this is telling us is it's unlikely to dissolve, and what we know from the real world is that it definitely does dissolve very readily. And we'll see in the next video of this series about why that is, why some endothermic reactions actually happen what we call spontaneous, without us having to actually put any energy in. An endothermic reaction that requires some energy takes place spontaneously. It's something called entropy that is going to dominate that, and we'll see that in the next video. Now, when we think about our bonding, sometimes there is a large discrepancy between the value of the lattice formation entropy that we work out using experimental values, our Born-Haber cycles, and the value that you can calculate theoretically. Obviously, the ideal scenario is that your theoretical value very much matches the experimental value. And for some cases, they're very close. For other cases, there's a really big difference between the two. And the reason for this difference is actually because of polarization. Now, we've talked about polarization in other videos on this channel to do with the bonding in different types of structures, particularly covalent structures. We can get polarization. And that's the really key thing. When we think back to our covalent structures, if we have polar bonds, we have this unequal sharing of electron density because of different electronegativities. When we think about polarization in ionic compounds, it's something kind of similar. And what actually happens is we have ionic compounds, things that we think of as being, actual physical transfer of electrons and pure electrostatic attraction, having a degree of covalent bonding. So while it's an ionic compound, there's a little bit of covalent bonding present in there as well. Now remember what we mean by covalent bonding. Covalent bonding is the sharing of electrons. We're not actually giving electrons away and taking them, we're just sharing them between. Now this can actually happen, and the way this actually happens is by remembering that our electrons really aren't discrete little particles, but they are electron clouds. They are this cloud of negative charge. If I have a pure ionic case, let's imagine it's just purely ionic, no covalent bonding at all. Our electron clouds would be perfectly spherically symmetric. They'd just be a sphere around our nucleus, around our ions. And that's a top example here for this zinc and selenium. You can see that we have these perfectly spherical shapes. That would be pure ionic. Now remember that if you go back to the video that looked at covalent bonding, we'll have seen some electron density maps. And we'll have seen that example for the pure ionic sort of matches a little bit what was seen for a pure covalent, this idea that we have kind of a perfectly symmetrical distribution of electrons. However, if we had a polar bond, say for example an HF covalent bond, because fluorine was so much more electronegative, it sort of pulled all the electron density towards itself, and you ended up with this very distorted shape of the electron density, with lots of it over by the fluorine and not much of it over by the hydrogen. And we can have this idea if we think about these electron clouds around our ions. If we have some distortion, you can see that typically the shape of the zinc ion electron cloud doesn't change. We'll get onto that in a moment. What does change is our selenium ion, 2- ion. You can see that going from pure ionic to some distortion, there has been this kind of stretching of that. It's no longer a sort of spherically symmetric shape. It's kind of been elongated a bit, squished a bit. And then this goes all the way down to having a covalent degree of bonding. You can see that in that bottom example, that selenium has been stretched, has been distorted so much that it's actually started to overlap with the electron cloud on the zinc. And remember that covalent bonding essentially is sharing of electrons. What we mean by that is that electron clouds, electron density, overlap. And so here we have some covalent bonding, some covalent degree of bonding within an ionic compound. Now what we actually mean by this is something called polarization and polarizability. So the anion, the selenium in this case, we say can be polarized. It can have its electron cloud distorted. And this is true for anions. Anions can have their electron clouds distorted. They can be polarized. For this to be really, really noticeable, what you want is an anion that is very large in size and has a high charge. Again, essentially it's to do with electrostatics for the charge, but the size part of it comes from the fact that if it's very, very large, it tends to be that the electron density is quite sort of diffuse. It spreads out quite far anyway. It's much easier to distort. For the cation, we say that the cation is polarizing. So it polarizes the anion. And so the electron density, so the electron cloud around our cation doesn't tend to change, but it is the thing that causes the distortion of the anion. And for our polarization, what we want for our cation here, for it to be really good at polarizing, is we want a small size and a high charge. So again, the charge is electrostatics. The small size, similar to what we've seen before, if it's very, very small, it can get very close to the anion. It can approach it much more closely, and therefore it's got much more chance of already overlapping with that distorted electron cloud. And we can sort of see maybe some kind of slight similarities and differences here between the trends in lattice enthalpy. So remember that for a smaller ion, we said it was a larger lattice enthalpy. What we really mean is that if it's a lattice enthalpy of formation, it's a bigger negative number. If it's a lattice enthalpy of dissociation, it's a bigger positive number. And also, the bigger the charge, the larger that lattice enthalpy is. And if we're talking about formation, more negative in that case. And so we can see some examples down at the bottom here, where we've compared these ionic compounds, and then we have our experimental value that we've calculated from our Born-Haber cycle, and the 100% ionic bonding, this theoretical model. So the theoretical calculations don't include the fact that there's some covalent bonding. They're assuming something that we call the perfect ionic model. I've shown this at the bottom left here. What we're assuming in the perfect ionic model is that there's no covalent interactions. It is 100% ionic. For this to happen, there can only be electrostatic forces of attraction. Our electron density can't be distorted, and our ions are these perfect spheres, these perfect hard spheres that can't be distorted. And so the experimental value is what we actually calculate from the Born-Haber cycles, and typically there's a discrepancy. And you can see for some cases, for example, lithium fluoride or sodium chloride, that difference is very, very small. Take sodium chloride, the difference is only 3 kilojoules per mole. So typically, what we'd say is that sodium chloride is really kind of 98, 99% an ionically bonded compound. But there's a very small percentage of it that accounts for covalent bonding in that molecule. So even the kind of prototypical example of what we talk about for an ionic compound, sodium chloride, actually isn't 100% ionic. You can then see that if we go down to some other species, such as the cadmium diiodide or silver chloride, that now you can see we have really quite big differences, especially for the CDI2, a huge difference between the experimental value and the calculated value. Now, why is it so big compared to something like sodium chloride? Go back to the trends in polarization. The iodide anion is huge. It's really big. So that's really good. It's got a large size and a high charge. The cadmium ion is very, very small. It has a high charge and it's very small. It's much smaller than, for example, the sodium is, and the iodide is much bigger, for example, than the chloride is. Hence why we get a much bigger change in those values. So the reason that an experimental value will be higher than the theoretical value is because of this extra covalent bonding, because of polarization. And so what this actually means is that bonding really is a spectrum. Over on the left, we have 100% ionic. Over on the right, 100% covalent. Well, 100% covalent exists. That's a bond between two identical atoms. So, for example, an HH bond, an FF bond, OO bond. Between the same atoms, it has to be 100% covalent, 50-50 sharing of those electrons. We can then start to work our way back to the left, and as we go from right to left, we're increasing the amount of ionic character. And we know that from our talking about polar bonds and stuff in previous videos, that we can get covalently bonded molecules that have a degree of ionic character to them. They have this unequal sharing of electrons. And then it goes all the way to the other end. But the key thing is that a perfect ionic 100% doesn't exist. It's theoretical. Even these examples of like sodium chloride, lithium fluoride that we think of as being very, very ionic compounds have some degree of covalent bonding. And the final thing to talk about is mean bond enthalpies. So we've talked about these already in the energetics part of these videos. But the lattice enthalpy is a measure of our ionic bonding. The more negative the lattice formation enthalpy, what we mean by that is the more energy is given out when we form our structure. And then conversely, if we turn that on its head and we go to the lattice dissociation enthalpy, the more energy that is required to break that structure apart. So lattice enthalpy is our go-to bit of data for ionic bonding. Bond enthalpies give us a measure of the strength of covalent bonding. If you remember back to the video when I talked about bond enthalpies, I said that bond enthalpies, if you think back to our definition, it's only applicable to covalently bonded structures. It's only the definition of it was that we broke our covalent bond in the gas state homolytically, 1 electron to each. The key things really though is that it's in the gas state and that it's for a covalent bond. You'd never find a bond enthalpy for an ionic bond or a metallic bond. Here though, with lattice enthalpy of formation and lattice enthalpy of formation, we have this measure of ionic bonding as well. And again, remember that bond enthalpies actually refer to a specific bond in a molecule, and that actually these enthalpy values have a slightly different value depending on what type of molecule they're in, and the functional groups we have, the environment of the bond. And so typically we use mean bond enthalpies, which are the enthalpy for a particular type of bond, say a CH bond, but averaged over a range of different compounds. And I won't go into too much detail about it, but we remember that if we're calculating enthalpy changes using mean bond enthalpies, the mnemonic we can remember is BERP. So if we're given bond enthalpy data, we do reactants minus products. So the reactant bond enthalpy, the sum of those minus the sum of the product bond enthalpy. And the key thing that we've said before is that if we use mean bond enthalpies, again, we only get an approximate value for an enthalpy change. So the actual real value of that enthalpy change that you can work out might be different. So if you calculate it using Hess's cycles, using enthalpy of formation, for example, you're likely to get a different answer than if you use mean bond enthalpies, because the enthalpies of formation are actually to do with the specific molecules that are involved in the reaction, whereas your mean bond enthalpies are over a range of different compounds. They're an average number. So have a go at this question if you'd like, to do with calculating the enthalpy of solution for KBr, and then will it dissolve? And so use the data in this table here at the bottom, and pause the video, and the answers will be on the next slide. So to calculate this value, we need to draw out our Born-Haber cycle. Again, I'm going to start off by drawing my KBr, my solid ionic compound, at the bottom here. Then I'm going to think about the steps I need to dissolve this up. So I need to break up the ionic lattice. That's our lattice dissociation enthalpy. And I need to then hydrate the separate ions. So hydrate the potassium ion, hydrate the bromide ion. And this will be the same thing as just doing the solvation enthalpy. Remember, our solvation enthalpy is going from the solid ionic compound to the aqueous ions. And so the first thing I'm going to do is think about breaking up my ionic lattice. This is my lattice enthalpy of dissociation, the positive number. It's endothermic, so my arrow goes up. And so I have plus 679 kilojoules per mole going up. Remember, lattice dissociation takes 1 mole of the solid ionic compound, breaks it up into the gaseous ions. This is again why the definitions are so important to learn, because they can be really helpful. And then once we have our gaseous ions, the hydration enthalpy, remember the hydration starts from the gaseous ion and goes to the aqueous ion. We can draw these. These are exothermic changes because we're forming those ion dipole forces as our water molecules cluster around the ions. And so we draw the 2 arrows going down, one for the hydration of the potassium, one for the hydration of the bromine, both bromide and ion, both negative enthalpy changes. And then that leaves us with our solution enthalpy. Again, I've drawn it here as a double-ended arrow because at this moment in time, we don't know whether whether the line that has the solvated ions is actually above or below that solid ionic compound, i.e. we don't know whether our solution enthalpy is positive or negative. So if we can't go from the KBr solid to the K plus and Br minus as aqueous ions, we apply Hess's law. The overall enthalpy change will be independent of the route we take. And so instead we can just go around the other way. That's going up, just breaking up the ionic lattice, and then down, hydrating the ions. Remembering that if we go with an arrow with the direction of it, we keep the sign. If we go against the direction of an arrow, we have to flip the direction of that arrow and flip the sign of the enthalpy change. And we just add all of our enthalpy changes together. So I'm going to go right from the bottom right to the top. That's our dissociation enthalpy. So plus 679 because I'm going with the arrow. Remember, if you were given the formation, you'd have to flip that arrow and flip the sign of that enthalpy change. And then I just add the 2 hydration ones together. So it's plus minus 322 plus minus 355. And when you do that calculation, you end up with an enthalpy change of solution for KBr to be plus 22 kilojoules per mole. And so then again, remember that if we have a negative solution enthalpy, an exothermic change, we're saying that the attraction between the ions and the water is greater than the attraction between the ions and the lattice. It prefers to be dissolved rather than as the solid compound. If we have a positive solution enthalpy, like we do in this case, an endothermic solution enthalpy, well, the attraction between the ions and the water is less than the attraction between the ions in the lattice. So it prefers to be the solid ionic compound rather than being dissolved. And so here, this is technically an endothermic, it's positive 22, and so it's unlikely to dissolve because our lattice enthalpy is actually greater than our solution enthalpy. However, as we talked about in the start of this video, entropy may cause it to actually be soluble. We may have this endothermic reaction actually being spontaneous and actually happening, even though we're not putting any energy in, technically. But we'll see entropy in the next video of this series. The final thing I wanted to show you was that you can actually do these solution enthalpy questions as Hess's cycle. So if you're not a particular fan of doing it as a Born-Haber cycle, you can actually do it as a Hess's cycle. Remember that a Born-Haber cycle is just basically a bigger version of a Hess cycle. And so the way to do it this time is I've got my reaction along the bottom, that's my KBr solid ionic compound, dissolving to form the K plus and Br minus aqueous ions, that's our solution enthalpy. And then again I can just think about actually how do I do this reaction? How do I solvate, how do I dissolve up my KBr? Well, first of all I'm going to have to break it up into its ions, and here I'm going to break it up into the gaseous ions, that's our lattice dissociation enthalpy definition. So KBr solid to K plus as a gas, Br minus as a gas, plus 679. And then I'm going to put both of my hydration enthalpies into one arrow. It's just the sum of the hydration of both the potassium and the bromide ions. And so we have the minus 322 plus the minus 355. That gets us from the gaseous ions to the aqueous ions. And then we just use Hess's law that we've always used, that if I can't go along that arrow along the bottom, I have to go up the arrow on the left, down the arrow on the right. So it's just adding them together and doing the same sum, again, gives you plus 22 kilojoules per mole. So thank you for watching this video. You can find many more videos like this on my YouTube channel. If you found the video helpful, please consider leaving a review on a tuition website. I offer online tuition for chemistry, so please check out my tuition pages for prices and how to contact me. And if you need any more help with your chemistry, you can always feel free to drop me an email. I'll be happy to help.